Welcome back. This week we look at shear force and bending moment diagrams. Now to get started, we're going to look at shear, the principle of shear, and I'd like you to get hold of one of these devices, a pair of scissors, which is probably close at hand, and let's talk about that for a moment with a view to understanding shear slightly better. I'd like you to have a look at what's going on here along these blades. Try and look carefully at the shape of these blades, and then take a scrap piece of paper and cut it, and we're going to analyze what happened as you cut that piece of paper. Now, a popular misconception out there is that a cross section through a pair of scissors would yield a shape like this, and in fact when your scissors are blunt and you wish to sharpen them, you could use a grindstone to sharpen the blades. And if you were to sharpen them in this fashion, you would find that they cut very, very poorly, if at all. Okay, so this, as I've drawn here, is most definitely not the shape of scissor blades, the desired shape, because that would not work. They don't cut as knives. Instead, they look a bit like this over here. So when you sharpen a pair of scissors, you ensure that you get an almost flat surface there with a keen, well-defined edge over here, and you normally give it a slight relief angle like that and like that. The green two lines indicate the piece of paper, and that is the two blades approaching the piece of paper, ready to cut it. And here they have cut the piece of paper. Now I use the word cut, but in fact we should say sheared the piece of paper, because that's exactly what's happened to the piece of paper. It's a right hand half. This half here has been pressed upwards, and the left hand half has been pressed downwards, and there the failure occurred. And in fact the piece of paper did not get cut. The piece of paper failed in shear, and there the pieces of paper fall to the ground and the two blades pass by each other, their work having been completed. So that is the concept of shear and shear force, and in this case shear failure as well. And that concept of shear we're going to use on other mechanical engineering devices such as beams. I would recommend that you look at this series of videos and find the one relating to shear force and bending moment, because it seems to explain the concept very well. So in this section of work we are going to be looking at shear force and bending moment, and we're going to do them together because they are completely different concepts, but they are normally used at the same time, so we're going to handle them together. And we're going to start with this very simple beam ABC, which is loaded at a point somewhere along its length, 2 meters from the left-hand edge, with a downward point load of 10 kilonewtons. It is simply supported at A and at C. The magnitude of the left support reaction at A is L. There's an upward arrow there and an upward arrow over there. So to find the values of L and R, in other words the magnitude of the two support reactions, we take moments about appropriate points. Now let's start by taking moments about A, sum of moments about A, and we find that R times 5 meters is an anti-clockwise moment, and it must be equal to the only clockwise moment, which is 10 times 2 meters, and that would allow you to solve for R at 4 kilonewtons. So over here R is 4 kilonewtons upwards. Take moments about C and do the same to find L at 6 kilonewtons. So now we have the two support reactions, 4 kilonewtons upwards at C and 6 kilonewtons upwards at A. Please be careful with the notation. A, B and C are place names. L and R are magnitudes of forces. So we don't take moments about L, for example. We take moments about A, and we work out the magnitude of L. So let's just get that sorted out from the outset. Now this beam, as we see it over here, is in equilibrium. It is standing still under the influence of 1, 2, 3 forces acting on it. So because it's in equilibrium, we can consider all of it or parts of it and their equilibrium. So if we were to consider this portion of the beam from an arbitrary point over here to the left, this portion over here, let's just focus on that. If it is to be in equilibrium, it follows that because it has a 6 kilonewton upward force acting at point A, there has to be a 6 kilonewton downward force coming from somewhere to keep it from rising, in other words, to keep it in equilibrium. Now, the only contact it has with anything else is the right-hand portion of the beam, in other words, this piece over here. So the right-hand portion of the beam must be applying 6 kilonewtons of downward force to the left-hand edge of the beam. And remember, Newton's law said for every force there's an equal and opposite force. Well, that's exactly what's happening. To maintain equilibrium of the left-hand portion, the right is pressing the left down with 6, and conversely, the left is pressing the right upward with 6. And that is what's keeping the equilibrium. Now, if you zoom in to this portion over here, and you have a look at what's happening, effectively this piece of beam on this plane over here is being sheared because we have 6 down and 6 up. So we have this shearing action, much like the piece of paper under the influence of the scissors being sheared. This beam, as it stands over here loaded with these 3 forces, is feeling shear all along its length, and at this point where we are now focusing, it is experiencing 6 kilonewtons of shearing action. And in fact, everywhere from A all the way through to B, all places along this particular beam are feeling that very same shearing effect. So the shear force remains constant at 6 kilonewtons everywhere between A and B for this beam. And when we get to plot the shear force, we do it with a shear force diagram, and we draw the beam, and directly beneath it we draw what is effectively a graph of shear force. And as you can see, everywhere from A to B is experiencing a consistent 6 kilonewtons of shearing effect. So a slightly more formal definition of what we've just done is that the shear force at any section of a beam is the algebraic sum of all the vertical forces to the right or left of that section. So an easy way to do this is to go to the beam, place your hand on the beam such that you expose one side and cover the other side. In this case, let's pretend that my hand is over here and I'm covering this portion and exposing this portion. I then look for the algebraic sum of all the vertical forces to the right or left of that section. So in my case, let's take everything to the left of where my hand is, and all I can spot is one upward 6 kilonewton force. So that is the shear force at that plane of the beam, at that cross section of the beam. Now we need a sign convention, and that is going to be used as follows. Any upward effect produced by a force is said to be positive. So upward effect suggests that what we saw here with the left-hand side exposed and the 6 kilonewtons pressing upwards is an upward effect. So we're going to refer to this as positive shear. And you'll see when we get to the drawing, the shear force diagram, we do indicate that as positive. In other words, above the line. But now the confusion comes in because there was also what appears to be downward effect at that very same point. Now, to stop that from being confusing, the following is applied. So here's how that is handled. To overcome this confusion, the sign of the shear force at any section is always determined by considering that part of the beam to the left of the section. So when we placed our hand here and we exposed this piece, we considered everything to the left of our hand, and if its effect was upward, then it was positive. So work to the left. Now an easy way to handle this is to simply start at the left hand end of the beam and work your way across to the right hand side. So in our case we had 6 kilonewtons initially upwards, so we go up to 6, and then from A to B the shear effect or the shear force stayed constant at 6. We go across, and then we encounter a 10 kilonewton downward force. So plus 6 with minus 10 applied to it would then knock us all the way down to 0 and beyond to minus 4. So plus 6 minus 10 takes us to minus 4. And then from B to C we stay constant again. And then we get to the end over here and we encounter a 4 kilonewton upward effect, which takes us from minus 4 conveniently back to 0, which is correct because for this simply supported beam, the shear at the ends is 0. So that takes us back to 0, and then we know we are correct as well. Next, we're going to be looking at UDLs. Now, a UDL is a uniformly distributed load. Now, a very easy way to understand the concept of what a uniformly distributed load is to consider a beam such as the one I've drawn here. And instead of a point load, which we understand by now is a force applied at one infinitely small spot somewhere on the beam, that is called a point load. Now, different to that is a uniformly distributed load. So if you were to go and get hundreds of small packets of, or little plastic packets, and put something heavy in each one, maybe some soil, and you were to package all these little packets and tie them closed, each one with some soil in it, and then you were to carefully take each one of those packets and load it on the beam, tightly one next to each other. It would effectively be lots of little point loads that you were applying to the beam because of their own weight pushing down. But if they were packed tightly enough together, the beam would actually feel it as a distributed load, or what we're going to refer to as a uniformly distributed load. So we're going to draw that as follows. This symbol that you see like this is going to indicate a uniformly distributed load. And it is normally going to be given as so many newtons per meter. So you'll take the span of the UDL, however long that is, and you'll multiply it by this value here to get the total effect. So let's look at shear force and UDLs and how they work together. So here we have a beam once again. This one is 6 meters long, supported at point A and point B. There's an upward arrow there and an upward arrow there, being the support reaction at A and the support reaction at B. And there are no other point loads on the beam, but there is a UDL running, in this case, the full length of the beam. And we are told its magnitude is 2 kilonewtons per meter. So the total effect on the beam would be 2 times 6, which is 12 kilonewtons of downward force. But that downward force is evenly spread out all along the length of the beam. Does the beam feel shear? So what we do is we start out exactly like before. We work from the left-hand side, and we start with the 6 kilonewtons that the beam feels at its left-hand end. We draw that in on our shear force diagram. And then as we slowly slide our hand to the right and expose more and more of the left-hand side of the beam, we would have a cumulative effect of lots of tiny little loads as we move along, which is essentially what the distributed load is. And that would knock our line down, 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 further down, further down, further down, exactly as the point loads did in the last example. But this is progressively, smoothly applying those consistently all the way along. And what it results in is a straight line that descends. And it descends according to the rate, the size of this UDL, until we get right down to this point, where we experience the final 6 kilonewton upward support reaction, which takes us back to 0, and then we know we are correct. Now, what happens if we have UDLs as well as point loads on the same beam? Well, this little example is going to show us how they work together. So we must sketch the shear force diagram for the following loaded beam, indicating all important values. And here is the beam. It has a small UDL over here between points C and D, and it has a point load of 6 kilonewtons at B. First step is to work out the support reactions as before, the values of L and R in other words. So summing moments about A, we find 7 times R, 7 meters times R, being an anti-clockwise moment, is equal to 6 times 3 plus 2 times 3 times 5.5. Now let's look carefully where that comes from. 2 kilonewtons per meter multiplied by the 3 meters that it acts through, multiplied by 5.5. Where does the 5.5 come from? Well, that is the distance from A to the mid-span of the UDL. Listen carefully to the words, to the mid-span of the UDL. This is the span of the UDL. The mid-span is a point halfway along its length. In other words, 1.5 meters from C. Half of 3 is 1.5 meters. So from A, we have 1.5 meters plus 1 meter plus 3 meters. Gives you 5.5 meters. And that is where this moment arm comes from. So it follows that R is 7.29 kilonewtons. Then take moments about D. We have 7 times L, 7 meters times L as a clockwise moment is equal to 6 times 4 meters as an anti-clockwise moment, plus 2 kilonewtons per meter times 3 meters times the distance from the midspan of that UDL to point D, which is half of 3, which is 1.5 meters. That's where that comes from. And incidentally, that is a plus sign there, not a multiplication sign. Now for the shear force diagram, starting from the left, we encounter 4.71 kilonewtons, which takes us from the 0, which would be the shear force at the end, and we go up 4.71. The reason for up is an upward effect is deemed positive, as you will remember. From A to B, there are no UDLs, so the shear force stays constant at 4.71. We then encounter 6, which takes us down to below the line at minus 1.29. So 4.71 minus 6 takes you there to minus 1.29. B to C, once again, no UDL, so we stay level at minus 1.29. And then we start to dip progressively. Remember, the UDL is applied at the rate of 2 kilonewtons for every meter. So you can simply work out that you have 3 meters, 2 3s are 6, and you know you're going to end up 6 lower than you were over here. So you were at 1.29, plus 6 is going to take you to minus 7.29, which is down here. And then finally you finish off with a plus 7.29, which shows you that you're correct, and you end up back at 0. And there is your shear force diagram. Now earlier we looked at the beam in equilibrium with regard to upward and downward forces. Now we're going to look at the rotational equilibrium of that very same beam. Now rotational equilibrium is essentially what moments are all about. So we're going to look at the beam, and we're going to look at how it is held in equilibrium under the influence of rotational effects. Now that upward force at A was causing a rotation clockwise. If you were to put your hand here and expose the left-hand side of the beam. Now for equilibrium, something must be applying an opposing moment, in other words 6 kilonewton meters anti-clockwise. That is assuming we're talking about 1 meter from the end, and that is coming from the right hand side of the beam for the equilibrium. But really it's a simple matter of doing it as follows. Simply place your hand on the beam wherever you want to know the bending moment. So let's say we want to know it 1 meter from the left hand end. So we place our hand here 1 meter from A, exposing the left hand side, and we say, right, what force do we see to the left? Well, we see a 6 kilonewton multiplied by 1 gives us 6 kilonewton meters at that cross section. And you can do the same for absolutely any point along the beam, and you can consider the left hand side or the right hand side exposed. As far as sign convention goes, a little bit like the shear force concept, it says a bending moment is positive if the force producing it tends to bend the beam upwards. So let's start with this little example, which has only point loads on it, and let's try and draw a bending moment diagram. So here's the example. First step is to find the support reactions as usual. So we must find the value of L and R, and by now you should be comfortable with that. You take moments about an appropriate point. In this case I've chosen A to eliminate this force otherwise I have two unknowns. So if I take moments about A, I effectively eliminate one of the unknowns and leave only R as an unknown. So with my finger on point A, I say 8 times R, 8 meters times R is an anti-clockwise, is equal to 12 times 6 plus 4 times the full distance back to A, which is 11 meters, and I can find R at 14.5. Similarly, take moments about C to eliminate the other unknown, and I find L at 1.5 kilonewtons. Now we are aiming at drawing a bending moment diagram, but as we said earlier, we normally have shear force and bending moments working together or used at the same time. So let's start by working out drawing the shear force diagram first before we do the bending moment. So there is the beam with all the forces applied to it, because we now know all the values now, and we start with the 1.5 up at the left hand side, and our shear force diagram, this one here, starts at 0, goes up 1.5. And then between A and B there are only point loads, there are no loads, and there's no UDL, so we simply stay constant at 1.5. We encounter a 12 kilonewton load at B, which takes us from plus 1.5 to minus 10.5. B to C, no loads again, we just stay constant at minus 10.5. There we encounter 14.5 positive, so up we go, puts us at 4. Across we go at 4, and then we encounter the final 4, takes us back to 0. So that is the shear force diagram sorted. Now let's do the bending moment diagram. Now the bending moment at the end of a beam that is simply supported is 0. Okay, there is no bending effect at the end of a simply supported beam. Cantilever, built-in cantilever is a different story, but if it is simply supported, there's no bending effect here. But as you move along the beam, there is more and more bending effect. So what is the bending effect at this point here, for example? Well, as we said before, you simply place your hand and expose one or the other side of the beam. In this case, I'll expose the left-hand side because it's the easier side. So my hand is here, and it is obscuring all of this, and it is exposing this piece here. What is the bending moment? Well, we've got 1.5 times 2, which would be 3 kilonewton meters. So we start by drawing our bending moment diagram with a 3 value at this point. And we progressively work along the beam. We work out the bending moment here, which would be 1.5 times 4, which gives us 6. And we continue, and at point B we would have 1.5 times 6, which puts us at 9. Now it is a straight line, as you'll see. You can prove it to yourself by working out those values and plotting it. You'll see that that is a straight line. Next is to work out other significant points, for example C. So place your hand on C and expose either the left or the right hand side of the beam. In my case, I'm going to use the right hand side because it's simpler. So this side is covered up and this side is exposed. My hand is on C. I see 4 times 3, which is 12 kilonewton meters of bending moment, and the force producing the bending effect is down, which makes it negative according to our sign convention. So negative 12 plotted for point C. And because there are only point loads in this example, it is all straight lines, so you can simply join the dots with a ruler, and there is your bending moment diagram, and there's your shear force diagram for this simply loaded beam. Now comes the interesting part. When you have UDLs and you are working out bending moments, the bending moment curve is no longer a straight line. It is going to have a curved shape to it. And to illustrate that point, here we have an example of a very, very simple symmetrical beam supported at A and B with a consistent 3 kilonewtons per meter UDL across it. And then what we're going to do is we're going to work out the bending moment at various points along this beam and work them out and plot them and note what shape we get. Now I'm going to illustrate the method of working out each bending moment, and then you can attempt them yourself and fill in that table below. But essentially the way it works is if you want the bending moment at section XX, which is in our case distance x from point A, you are going to replace the piece of UDL to the left of your hand, assuming that that's the side you're working with. The UDL to the left of your section would be x meters long. So you would apply the quantity or the magnitude of the UDL being 3 kilonewtons per meter. You would multiply 3 by x to get the total value, because remember it's 3 per meter and we have x meters. So the total force acting on the beam is 3 times x. Where does it act? Remember those words mid-span? Well, the piece in question is this little piece over here. Its span is x. So mid-span, mid means half. Mid-span would be x over 2. So all we do is we replace the UDL in our minds with a force equivalent to its full magnitude, which would be 3x. Where do we place it? At mid-span, in other words here. We make it a dotted line to show it's an imaginary thing that we are using. And we simply treat it then like a point load from that point on. So the bending moment at XX is simply 3x times x over 2. 3x times x over 2. But that's only the bending moment as a result of the UDL. If we are taking bending moment at XX, we mustn't forget that there's also 12 times x. So the full bending moment at section XX would be as follows. 12 times x, remember positive or force tending to produce the bending moment. If it's upwards, we get a positive sign, so there's positive over here. And then the minus 3x squared over 2 we spoke of moments ago would be the resultant bending moment of the UDL. So bending moment at XX is 12x minus 3x squared over 2. So let's take various values of x, starting with 0, then go 1, 2, 3, all the way through to 8. And then I want you to work out the corresponding bending moments and fill them in this table here. And hopefully you're going to get these values here as the bending moments at those various distances from A. And once plotted on a graph, you would find this shaped graph. So clearly you can see that when a bending moment is involved, even if it is mixed with other point loads, we end up with a curved result for our bending moment, no longer a straight line. And of course the shear force is no longer a horizontal flat line, it is now a sloping straight line. So there is the end result for the example that we just did. There's the beam, there's the descending line showing shear force, and there is the curved line showing bending moment. So it's very important that you get comfortable with these two diagrams at this point. And the shape of the bending moment line is in fact parabolic. It's a parabolic curve. Now with the example that we've just done, the support reactions were at the ends of the beam. Now things get interesting as those supports move inwards. So let's take the support reaction at A and shift it inwards a little bit, and let's take the support reaction at B and shift it inwards a little bit. And let's use the same beam with 1 kilonewton per meter UDL along its full length, but let's shift the support reactions to 1 meter from the ends, 2 meters from the ends, and 3 meters from the ends. And you can follow the exact same process as before and draw our various bending moment diagrams. And you're going to find the shapes that result here. I want you to try those yourself. Now when you do these and you split it up into little sections, you would be able to determine whether the shape is curving that way or curving this way. And an easy way to remember that is as follows. If the UDL is on top, as in the case of these, all the curves will bulge, I call it skywards, so they go this way. If the UDL was under the beam, which is not the case here, then the curves would bulge the other way. And that saves you a lot of time because you can simply find the values at the start and end of each curve and then simply draw in the curve either bulging skywards or downwards. That is, if you don't need the exact values along the bending moment, you just simply need to find the end points and then sketch in the bending moment curves, bulging this way or that way, depending if the UDL is above the beam or below the beam. While we're here, let's talk about point of inflection. This is any point on a beam where the bending moment is zero, i.e. where the bending moment curve crosses the zero line. So in our case, there are two of these with a point of inflection. This first one has 2 points of inflection, there and there, where the bending moment crossed the zero line. Here is also a zero, and this one doesn't have any of those. So here is an example that you need to work out. It says draw the shear force and bending moment diagrams for the following loaded beam, indicating all important values. If there happens to be a point of inflection or anything like that, that is an important value. Okay, so we have a point load of 10 and 12 kilonewtons, support reactions, which you must work out as before, a UDL between A and C, and this is a good point to stop the video and spend quite a while working this one out, and then compare your solutions for bending moment and shear force diagram with the solution which I'll give you a bit later on. Start by finding the support reactions. Let's take moments about B so as to eliminate L to get down to one unknown, and we find moments about B. 10 times 2 is an anti-clockwise moment, plus 3 times 2 times 1, that is the UDL of 3 per meter, times 2 meters, times 1 meter, which is the distance from the midspan of this little portion to B, plus 6 times R, which is your 6 meters times R, which is R times 3, 4, 5, 6 meters. So that's all the anti-clockwise moments handled. Now for the clockwise moments, so an equal sign, then the clockwise moments. 12 times 4.5, 12 times 4.5 meters, plus that last piece of the UDL, which was 3 per meter, times 3 meters, times 1.5 meters, which is the distance from B to the midspan of that portion. So we get R at 6.92. Similar fashion, moments about E to eliminate R and find L. Next is the bending moment at B. Put your hand on B, expose the easy side of the beam, which is the left by the looks of it, minus, because it's downward effect, times 10 times 2 would be the bending moment caused by the 10 multiplied by the 2, minus the UDL at 3 per meter times 2 meters times 1 meter, distance from midspan to B. So we have minus 26 kilonewton meters as a bending moment at B. Bending moment at C, place your hand here, expose the easier side, which is the right hand side by the looks of it. So we have minus 12 times 1.5 plus 6.92, which was R, times 3 meters. We've got the bending moment at C. Bending moment at D, very simple, it's just 6.92 times 1.5. And remember, the bending moments at the ends of the beam, because it is simply supported, are 0. So we can start by drawing the bending moment. It'll be 0 at each end and these various values along it. So a 0, a minus 26, a 10.38, and 2.76 there. Next is to decide where the bending moment will be straight and where it will be curved. Well, where there is not UDL, it will be straight, so you can simply join that point to that point with a ruler, and that point to that point with a ruler, and the reason for that is there are no UDLs in that area. However, between A and C, there are UDLs involved, so we need curves there. And all we've got to decide at this point is whether they curve skyward or downward. Now remember what I said, if the UDL is above, they curve this way. So that means that that would bulge skyward, as I call it. So this shape is bulging towards the sky, as is this one bulging towards the sky, and it ends over there. So a curve, and that will suffice. But now remember what this point is. Where the bending moment crosses the zero line, that is called a point of inflection, and that is considered an important point. So we're going to have to define in a moment exactly where this spot is. But before we do that, let's do the shear. Shear force, 10 down, starting from 0, 10 down, 3 per meter, takes us to minus 16. We encounter plus 30.08, puts us at 14.08, descending with a straight line all the way down to the end of the UDL. Work it out, you'll get to 5.08. Go across with a straight line, encounter minus 12, puts us at minus 6.92. Cross with a straight line, and 6.92 takes us back to 0. The nice thing about the shear force diagram is if you get back to 0, you know that all your values were correct along the way. Now for that point of inflection. All we know right now about the point of inflection is it occurs somewhere to the left of point C, and it occurs before we get to point B. In other words, it's somewhere between B and C. So let's call that significant point F, and let's come up with an equation for bending moment at point F. And let's give the distance from point F to the end of the beam as x meters. And let us expose, or let's put our hand on the beam at F, and let's expose this side of the beam and work out the bending moment at point F. So we have minus 10 times distance x as our first number. And then we have minus 3x squared over 2. Well, that is 3 per meter times x over 2, remember, because x over 2 would be the distance to the midspan, and that ends up as 3x squared over 2 plus 30.08 times x minus 2. Let's look where that comes from. 30.08 is the value for L times the distance from where it acts to where our hand is, which would be x minus those 2 meters there. And we can make it equal to 0 because we know at the point of inflection we're past the 0 line, so the bending moment is 0. So now we have all of this equal to 0. So we can simplify matters a little bit, and we end up with a quadratic equation, and we can solve for x. Remember how it worked? We had ax squared plus bx plus c equal to 0, and x was equal to minus b plus or minus root b squared minus 4ac all over 2a. Let's lay that out a bit more simply. In our case, the quadratic looks like this. So there's our a value, which would be 1, because there isn't a number there. Our b value is minus 13.386, there it is there, and our c value is 40.106. The quadratic equation says that x is equal to minus b plus or minus root b squared minus 4a times c all over 2a. So you can take that a step further. Minus times a minus gives you a plus 13.386. Minus 13.386 squared becomes positive. Subtract that from it and you get that inside the square root sign all over 2a, which is 2 times 1, so we just got 2 at the bottom. So now we have the plus option and the minus option, giving us answers of 8.858 or 4.528. Now remember that one answer will be possible and one will be nonsensical. So the reason I chose 4.527 rather than 8.8 is because 4.5 would appear to be possibly between A and C, in other words F, whereas 8 and a bit would be outside of the beam, which is impossible. So your answer is 4.527 meters to the point where the bending moment is 0. In other words, the point of inflection is at 4.527 meters from A. Right, here is another one for you to try on your own. Draw the shear force and bending moment diagrams for the following loaded beam, indicating all important values. So once again, stop the video now and spend some time getting this one correct before looking at the solution. Using what you learnt in the previous one, you should have had no problem finding the shape of the shear force diagram. There were no problems there. Also, the bending moment diagram should have been without a problem. Even the point of inflection, you were able to use exactly the same method as before to find the point of inflection. The only issue that you might have had difficulty was with where the bending moment peaked. And that you need to note that the bending moment works as follows. The parabola between A and B will be a maximum at point D, where the shear force is 0. So where the shear force line crossed the 0 lines up with the highest point of the bending moment diagram. You need to take note of that. And lastly, remember the shape of the bending moment was bulging skywards, and the reason for that was the UDL was above the line. This one is interesting in that you are given the bending moment diagram. The diagram below represents the bending moment distribution along a loaded beam. Portion CD supporting a uniformly distributed load only. So they're telling you that between C and D there are no point loads, only a UDL. From this diagram, sketch the loading and shear force diagrams showing all important values. So you've got to work backwards and find the loading and shear force diagrams. So essentially you use exactly the same methods, you're just working backwards to find the load that caused the bending moment. And once you have the various loads, you can then draw the shear force, knowing that between C and D it was having a UDL, so therefore it is sloping. You can draw in the UDL and even figure out its magnitude. So try that one. And once you're done, have a look at that solution. And another one to practice on. Number 4 is one where we have the supports at each end. Not quite at each end, they are moved in some distance from the end. Much like this situation that we had over here. And what they're saying is they want this value of bending moment to be as small as possible. Now as you can see, as the supports came in from each end, so this curve descended until it was way down here. Now if we want that bending moment to be numerically as small as possible, in other words, to cause the least bending on our beam, we had better get this, whatever the biggest minus number, it had better be equal to the biggest plus number. Here we have plus 4 and only minus 0.5. Here we have minus 2 and only 0. If we can shift this to be balanced, so we have as much minus as we have plus, then we will be getting away with a situation that has the least bending moment in total, be it positive or negative. So we want this situation where this value is numerically equal to this value here. So MA must be numerically equal to MC. That's what MA is if you expose the left hand side of the beam, or the right hand side, it's symmetrical. And that's what MC is equal to. Make the two equal to each other and you find that at 1.87 meters for X, you will achieve that situation. And another one for you to practice. There are the words. And there is the sketch of what's going on. So have a go at that. In your solution, you will probably have noted that the maximum bending moment is hard to define unless you remember that it occurs in line with the point where shear force was 0. So that's a significant point to note. Also that the UDLs curve skywards, as we said, so they curve that way. And between this point and that point, the shear force diagram is sloping and the bending moment diagram is curved where there is UDL. Where there is not UDL, it is straight lines. and there are 2 points of inflection, here and here, which you work out like that. So give that one a good go. Now here's our last one that we're going to finish off with. It is to do with an aircraft wing, which essentially is a beam. You can't see it, it's inside the wing, but there is a beam which is the primary structure supporting the rest of the wing. So if you look at it in side view, there is the beam, or the spar as it's called in an aircraft. And in this case it has an external lift strut, which we've drawn as a two-dimensional tension member over there. And you are given dimensions, and you are told to treat it as a simple beam. And there is a UDL in this case, which is the aerodynamic lift which supports the aeroplane. When an aeroplane flies, it essentially feels lift, which is in essence a force holding the aeroplane up as lots of little upward forces under the wing, which is a UDL. But in this case, the UDL is below the wing. Remember what that does to the shape of the UDL for your solution. And probably the biggest hurdle is just to work out the force components at this point. So make sure you get that right. And in fact, for part A, you've got to find the load in the lift strut. What tension force is in this member for equilibrium of this whole setup over here. That shouldn't be a problem. Next is the shear force diagram, indicating values at all points A to F, A through F on your diagram. Draw bending moment diagram, same thing. Determine the position of the point of inflection measured from A, if applicable. Okay, so that's your last one. Give it a good go. Stop the video now and have a look at the solution only when you have made a good attempt. Working out the force in the lift strut, remembering that it will be a tension member. Remember, 2 arrowheads towards each other. So we'll call that FGD, G to D. And when we come to use it on the actual beam, let's use components of FGD. And we were told that there's 30 degrees there, which means there's 30 degrees there. So FGD rotated through 30 degrees would give us FGD cos 30 down the spar, or the beam in this case, and the other component FGD sine 30. So those are the ones that you're going to use when you take moments for the actual beam itself. But to find the value of FGD, let's start by taking moments about A and looking at FGD sine 30 times 1, 2, 3 meters equal to 600 times 5 times 2.5. Now 600 is the UDL, so 600 times the 5 meters times 2.5, which is the distance to the midspan from A, would allow us to find FGD's value, the tension value in the lift strut, at 5,000 newtons. And similarly, we can take moments about F, and we can then find the support reaction at the end of the beam, RA vertical at 500 newtons. Then you need to work out bending moments at various points along the beam by exposing either the left or the right hand side, whichever is easier for you. Make sure you get those 4 values. Then we can plot the shear force diagram, starting with 0 shear force at A, going down to minus 500 immediately, and then adding in our other forces as we go along, remembering that we go from minus 500 and we climb at a rate of 600 newtons per meter, because that's the UDL, until we get to this point where we get FGD sine 30 taking us down to minus 1200, and then we climb again until we get back to 0 at point F. Then it's time to plot the various bending moments from the values that we have over there, and we will have a curved graph at all points because of the fact that there is UDL along the entire length. And the shape of the graph, remember, would bulge downwards because the UDL is beneath the beam. We saw that earlier on. And finally, one needs to pinpoint more or less where the point of inflection occurs, between where and where, so that you can set up an equation for bending moment at that point, and then go back and solve for the distance x, which in this case we're taking from A across to the point of inflection, and we're using it in that equation. Make sure you get the same equation. which turns out to be a quadratic, and you can find that the point of inflection is 1.667 meters from A. And this is a very important point when you are designing this wing spar, because that is the point where bending moment is 0.